Friends, let us now start some serious discussion on chemical reaction engineering, and we will do that by reviewing some of the undergraduate material, that is material I was referring to in my last lecture in your first course on chemical reaction engineering. But before actually we do that, last time I forgot to mention something. So, let me also highlight some of the good textbooks or reference books from which material for this lecture has been taken. The first book is a classical book by Aris, who was a mathematician turned chemical engineer, on elementary chemical reactor analysis. The second book you probably are all familiar with is the Fogler's book on elements of chemical reaction engineering, and this is one of the books where you have lot of material with which you can get hands on experience and so on. But more importantly, it is available as an Indian edition, so it is affordable. The third textbook which is also now available in India is actually a graduate level book on chemical reactor analysis and design by Froment and Bischoff. And the last book which I like is the book by Lanny Schmidt, and you might have noticed few references in my last class to material from this book. This book is interesting not only because it gives very good analysis of chemical reaction, reactor design and so on, but it is also good because it gives lot of practical examples. The chemistry part which I was referring to, chemistry is important. So, there is a lot of examples from real life chemistry examples, and so it is always interesting to relate things to actual practice. So, with this, now let us start reviewing some of the undergraduate material. So, what is this reaction engineering all about? And let us take an example of ethylene production. What you see here is actually a plant which is coming up in Abu Dhabi, which is going to produce about 1.5 million tons per annum of ethylene by steam cracking of ethane. So, while designing this reactor, what do we mean by designing this reactor? So, finally, at the end of this exercise, something like this comes up. So, let us say that we want to carry out this cracking of ethane, and typically it is carried out in a tubular reactor, multi-tubular reactor. So, what you see here outside as one long shell is actually having lot of tubes inside and some kind of a shell and tube kind of arrangement. So, we are going to produce ethylene in this reactor, and typical production capacity of each tube, I am not talking of each reactor that you saw in the previous photograph, but each tube is about 10,000 tons per annum. So, what happens in this reactor? So, some of the conditions that are specified is in the inlet of the reactor we have ethane and steam. Now, you may be wondering why steam, because steam actually does not participate in the reaction. The reaction is straightforward, ethane loses one hydrogen molecule to give ethylene, and so where does steam come into picture? We will try to find the answer to that question in due course. Then, for example, the feed inlet pressure is about 3 atmospheres, temperature is about 600 degrees or 700 degrees centigrade. Now, who told us to have inlet pressure of 3 atmospheres and temperature of 700? Why not 100 atmospheres and ambient temperature? We will try to find the answer to this question as well. Then we have a tube length of about 95 meters, and ethylene conversion or conversion of ethane, for example, about 60% from the entry to the exit. So, these are all typical design conditions that we have determined. Now, how do we come across all these conditions? We will try to review the material that we have already seen, which will partially answer these questions, and in due course of time some new questions will be posed and of course answered. So, how do we go about reactor design in general? So, this is our cracking of ethane to ethylene. So, we have one molecule of ethane giving rise to one molecule of ethylene and liberating one hydrogen. So, that is a dehydrogenation reaction. In a reactor design, what we typically do, and this you would have seen in some form or the other, is start with what is the stoichiometry of this reaction, that is one molecule of ethane going to one molecule of ethylene and so on. What is the conversion? What is the molar flow rates that are going in and out of this reactor? Develop some suitable kinetics of this process, so that we know what is the rate of reaction. Put these two pieces of information together in the form of mole balances, depending on the kind of reactor, whether we are doing a batch reactor or a CSTR or a plug flow reactor, there will be suitable mole balances and design equations. So, put all these information together and then come up with the reactor design. The reactor design per se involves conversion, finding conversion or finding volume of the reactor or length of the reactor, as we saw in the case of ethylene, what should be production rate, what kind of reactors we should use and so on. So, these are our design criteria. I do not mean to imply that for every problem all these will be considered. For example, in some problem we will be given that we want 60% conversion, what should be the volume of the reactor, or if we have an existing reactor of certain volume, what is the maximum conversion that is possible and so on. So, we have various different combinations of these all these different things. So, the starting point for us is this stoichiometry, and we will try to now represent our reaction in a more formal manner, so that we have the required stoichiometric tables and so on. So, let us see how we represent a reaction. What I will be doing is giving you some kind of a general picture and then illustrating it with a particular example. That is what I hope to do for all the lectures that we will be doing. Then we will be looking at extent of reaction and conversion and some thermodynamics and chemical reactions. Thermodynamics is very important for reactions, and we will try to see why they are important. So, let us start with the representation of a chemical reaction, and we will start with the simplest possible way we can do, and namely consider a single reaction. Since we want to keep our discussion little general, as I said, I will start with first general definition, and then I will go back to specific examples, and we will keep going back and forth, so that we are together. So, let us say that we have n number of different species, and we label them as A1, A2, A3, A4 and so on up to An, and we now want to write a reaction of this. So, let us take an example of a methanol synthesis. So, let us consider a reaction of carbon monoxide and hydrogen to give rise to methanol, and since this reaction has to be balanced, we need 2 moles of methanol, 2 moles of hydrogen to give rise to 1 mole of methanol. Now, this reaction involves 3 species. So, the N that we were talking in previously, N is 3, that is our number of species is 3 for this example, and let us call this carbon monoxide as A1, hydrogen as A2 and methanol as A3. So, I can immediately write this reaction as A1 plus 2 A2 giving rise to A3. That is a standard way of representation. But to make our representation more uniform, I am going to write the same reaction in yet another form, and that is A3 minus A1 minus 2A2 equal to 0. You will notice all I have done is kept the product as it is and bring all reactants onto other side, or from, that is what we normally write from left to right. I have just brought it on the other side and written this reaction as A3 minus A1 minus 2A2 equal to 0. When I write this reaction like this, I can now write a stoichiometric coefficient nu 1 A3 plus nu 3 A3 plus nu 1 A1 plus nu 2 A2 equal to 0 as yet another representation. All I have done is I have generalized this reaction by converting these coefficients which appear before A1, A2, A3 in form of nu 1, nu 2 and nu 3. Or in other words, I can write my generalized reaction now containing species, 3 species in this particular case A1, A2 and A3 as summation of the product of the stoichiometric coefficient and the corresponding species, and summing it over all the species that are present in the reaction and writing it as summation nu j a j, summation is over j going from 1 to 3 equal to 0. Notice that I am making my representation more compact as I am travelling down this slide. So, in general, if we have n species, I can write this reaction as j going from 1 to n summation nu j a j equal to 0, and this is my chemical reaction that I am going to focus on. The advantages of writing a reaction in this manner will become apparent as we continue our discussion. So, let us get back to our lecture. So, we have a single reaction between the n species A1, A2, A3, and we just wrote this reaction in a general form as summation nu j a j, j going from 1 to n equal to 0. So, that is our representation of my single reaction. Now, what happens if there are multiple reactions? And for that, what we will do is, let us say that I have this one reaction that we started with. So, let us label this reaction. I am going to call this reaction as reaction 1, and since it is reaction, I am going to just call it as R1. Now, let us say that in this reacting mixture there was some CO2 present in the reactor, and if that was present, then there is a possibility that CO2 also may react with hydrogen, giving rise to water plus carbon monoxide. Now, this is my second reaction. So, now I have two reactions which are possible, and both reactions are possible simultaneously. So, this is a now case of multiple reactions, which is what actually happens typically in any real chemical reactor. You hardly ever have a single reaction. So, you have multiple reaction. Notice here that earlier we had 3 species, now my number of species has increased. So, I have to change this number to account for the fact that there is another species carbon dioxide and yet another species water. So, my number of species is now 5. So, I have 5 species carbon monoxide, hydrogen, methanol, carbon dioxide, water, and between these 5 species there are 2 reactions R1 and R2. Earlier we had written our first reaction as A3 minus A1 minus 2A2 equal to 0. The second reaction now becomes A5. I will follow the same logic, that is keep products as they are. So, A5 plus A1, bring the reactants on the other side. So, minus A4 minus A2 equal to 0 as my second reaction. Now, what have we done? We have stoichiometric coefficients for all the species A1, A2, A3 for the first reaction, stoichiometric coefficient for all the species in the second reaction. So, now I am going to define my stoichiometric coefficient nu ij as the stoichiometric coefficient of species j in the ith reaction. So, for example, if I am looking at nu 1 2, that is stoichiometric coefficient of my second species in first reaction, second species which is hydrogen. So, my second species in the first reaction, that is minus 2. Similarly, I can define for all other species. So, for my ith reaction, I have a stoichiometric coefficient nu ij which is for jth species in ith reaction. So, what is my ith reaction now? My ith reaction is nothing but summation nu ij aj equal to 0. So, that is my ith reaction, and so this is my first reaction, second reaction and so on, depending on howsoever reactions we have. Notice here, while defining our stoichiometric coefficients, that is by writing reaction as left hand side equal to 0, we have followed one standard convention, namely if the reaction is, if the species is the product of the reaction, namely like methanol, the stoichiometric coefficient is positive. If the species is the reactant, the stoichiometric coefficient is negative. So, we follow this standard convention of positive stoichiometric coefficient for the product and negative stoichiometric coefficient for the reactants. So, this is my general ith reaction, and we now therefore have for multiple reactions, that is we are considering R chemical reactions in n species. So, that between A1, A2, A3, An, and we write this general representation as summation nu ij aj equal to 0, that is my ith reaction. So, I goes from reaction 1, 2, 3 up to whatever R reactions that I have, that is from for species in this summation from j equal to 1 to n represents my ith reaction, and we have R such reactions. Once again, the stoichiometric coefficient is positive if the species is a product of the reaction, it is negative if the species is the reactant in the reaction. Now, let us play around with this species little more and say that we have yet another reaction. So, let us say that these are the two reactions in these 5 species, and I am going to consider yet another reaction for my consideration, namely CO2 plus 3H2 giving rise to CH3OH, that is our methanol plus water. So, I am going to call this reaction 3. species are still 5, but I have 2 reactions. I am going to write third reaction, and you can think of many more reactions or reactions in many different ways one can think of. Do we really need this third reaction? I think by now you would have realized the way I wrote this third reaction over here was just adding these 2 reactions, and I wrote my third reaction. So, in that sense, my third reaction is actually a sum of these 2 reactions, or it is not really an independent reaction, but is a dependent reaction dependent on the other 2 reactions in the system. We naturally do not want such dependent reactions, because what is enough for us is the number of independent reactions, because any other reaction can always be written as a combination of the remaining reactions. So, how do we find out whether the given reaction? So, suppose I am given this set of reaction and I want to find out, is this reaction, are these all 3 reactions independent, or there is some dependency of one reaction on other two reactions. So, is this really an independent reaction, or is it a dependent reactions? So, how do I find that out? I find that out by going back to my mathematical representation of multiple reactions and focusing on this stoichiometric coefficient. In fact, we can write this stoichiometric coefficients for all reactions put together in a matrix form. That is, stoichiometric coefficients. So, what I have here is rows representing each of the reactions. So, this is reaction 1, this is reaction 2, this is reaction 3, and so on. And on the columns I have species 1, 2, 3, 4, 5 up to n. So, for our example that we previously saw, this is my first reaction, this is my second reaction, that is reaction between carbon monoxide and hydrogen. This is my second reaction, let us say, between carbon dioxide and hydrogen, and this is my third reaction, which is between carbon dioxide and hydrogen. Recall, we had written this third reaction as sum of these 2 reactions. For those who are mathematically inclined, you would have now figured out the way to find out the independent reactions. How? I will repeat, my third reaction is sum of the first 2 reactions, or in other words, my third row of this matrix. What is the dimension of this matrix? It is R by n. My third reaction, or my third row rather, is dependent on first 2 rows. And when you have a matrix, and when any one column or when any one row is a linear combination of other 2 rows, we always think of rank of this matrix. The rank of this matrix, stoichiometric matrix nu, is actually the number of independent reactions. So, if you go back to our set of reactions, write this matrix and try to find the rank. What rank do you expect? You expect rank to be 2. That means, there are only 2 independent reactions, and we need not consider the third reaction. It is important that we consider only independent reactions, and reasons for this are manifold. For example, if you are considering any mass balance or mole balance, or any other analysis with this stoichiometric matrix, why have something more than what you need? First of all, if you had a 3 by 3 matrix, by considering only independent reactions we would have reduced it to 2 by 3, and reducing dimensionality always is of great help. But there is another recent use of this stoichiometric matrix and its rank, and it comes from a very unlikely source, namely you and me, or to make it broad, living cells. What happens inside the living cells is there are numerous species, and by numerous I mean hundreds and thousands of species involved in numerous reactions, again hundreds and thousands of these reactions. So, in principle one can set up a stoichiometric matrix of this kind, and believe me, these are all pure chemical reactions. Well, we may call them as biochemical reactions because they are occurring in biological systems, but these are chemical reactions. So, we have this stoichiometry for all such reactions, and once you write this stoichiometric matrix, this matrix gives you lot of useful information about what is happening inside the cell. It tells you, for example, to give you just quickly the idea, if we say that our third reaction is dependent on first and second reaction, then suppose third reaction is addition of first and second reaction, then we also know that the rate of third reaction must be rate of first reaction and second reaction. Or in other words, if we are presented with such a matrix, it is enough to measure rates of these two reactions, we will always get the rate of the third reaction. So, information of this kind, which is all put together, one can say something what is called as metabolic engineering, flux analysis, metabolic control analysis. These are some of the fields in which this stoichiometric matrix is extensively used. So, now we move on to another idea, that is, we know how to write our reaction, and let us now go forward and actually do this reaction, and I want to know how far has this reaction progressed. So, I want to know the progress of this chemical reaction. I will again start with a single reaction, and then we will extend the idea for multiple reaction. So, how do we measure chemical reaction? So, the idea here is the following. Now, let us consider once again a single reaction, summation nu j A j equal to 0. I have omitted summation j for sake of simplicity, but it is understood that it is summed over all species, and let us say that this reaction is taking place in a closed system. I underline this idea that is it is a closed system, that is there is no exchange of matter of this system with its surrounding. That is what we understand by a closed system. So, let us say that I am carrying out this reaction in a closed system. I started out my reaction having Nj0 moles of species J in the initial startup of the reaction. So, I have species Aj and there are n such species, capital N, and small n is what I use to denote the number of moles of this species J, and another subscript 0 to note that it is initially present. And then let us say that this reaction progresses for some time t, and at the end of this time the number of moles of species J left in the reactor are Nj. So, we have two measures, moles initially present, moles present at time t. Then I define my extent of reaction, molar extent of reaction alpha, as a measure of progress of my reaction. And how is alpha defined? Alpha is defined as the ratio of the difference between the moles present at any time t, Nj, minus what we started out with, and ratio of this difference. So, this is actually how much has changed in the reaction. from its starting point to the stoichiometric coefficient of this species A j, that is nu j. Let me repeat, molar extent of reaction alpha is defined as change in number of moles of species J, that is N j minus N j 0 divided by nu j, the stoichiometric coefficient, and this is my first measure of progress of reaction. Let us look at some of the interesting properties of this extent of reaction. Once again, this is the definition of my extent of reaction. I want you to focus on the fact that I am always saying molar extent of reaction. That is, I am talking about a reaction now, not a species. In other words, this quantity alpha is defined for the reaction and not for the species. So, I could choose to write alpha as N j minus N j 0 by nu j for jth species, or N k minus N k 0 by nu k for kth species, and so on, and these all must be same, because it is the same reaction that we are referring to. So, since it is not alpha is not defined for the species, but for the reaction, I can use this quantity N j minus N j 0 by nu j or N k minus N k 0 by nu k, N L minus N L 0 by nu L, and so on, and they all must be equal. By using this equality and rearranging these terms, I can write now the number of moles of species K at any point of time is what we started out with, N k 0 plus the ratio of nu k by nu j, the corresponding stoichiometric coefficients, into the difference between N j minus N j 0. So, what has happened now? What we have done is we have defined the extent of reaction, used the fact that these are not specific to any particular species, but for a reaction, and now written the moles of species K in terms of difference in moles of species J, and this can be done for all species 1, 2. Suppose we choose J as 1. So, N 1 minus N 1 0 into nu k by nu 1 plus N k 0 will be N k, and this k will be for all 2, 3, 4, 5, 6 and so on. Or in other words, we can relate the change in number of moles of all species through this stoichiometric coefficients or stoichiometric relations. So, we have N k as N k 0 into nu k by nu j N j minus N j 0. Going back to this extent of reaction, notice that at the start of this reaction N j is same as N j 0, and as you would expect, reaction has not progressed, that means alpha is 0 at the beginning of the reaction. As the reaction proceeds, N j is different than N j 0. Let us say that species J that we are looking at is carbon monoxide or the reactant. So, if it is reactant, N j will be less than N j 0, because carbon monoxide has got reacted. So, this numerator will be negative, but so is the denominator, because since species J or carbon monoxide in our example is reactant, the stoichiometric coefficient is negative. So, we have a ratio of negative to negative quantities, which means alpha is positive. You can argue the same thing if J is product, numerator will be positive, denominator will be positive, or in other words, alpha is always positive. it is 0 in the beginning, it is positive for rest of the time that reaction is taking place. Alpha, that is the extent of reaction, is also an extensive property, that is it is related to the mass of the system. It is a extensive, you know, in thermodynamics you have studied intensive properties and extensive properties. Alpha is one of the extensive properties because it is in moles. So, mass associated with mass. Now, you may ask what happens if you have more than one reaction. Okay. We will come back to our multiple reactions little later, but let us define now another progress measure of progress of reaction, namely the conversion of the species, and we define conversion X again for the same reaction summation nu j A j equal to 0, that is my general reaction. I define my conversion as X as Nj0 minus Nj divided by Nj0. I am now defining conversion for a species. I am no longer defining for a reaction, but for a species as Nj0 minus Nj divided by Nj0. So, let us say that carbon monoxide is the species that we are referring to. So, my conversion of carbon monoxide is the initial moles of carbon monoxide I had minus the current moles divided by the initial moles, and this quantity conversion X goes from 0 to 1. It is 0 at the beginning and at best it can be 1. Now, we will see the cases where conversion will never reach 1, and perhaps some of you guessed it right. When it is a reversible reaction, your conversions may never go to 1, or in terms of percentage you may never have 100% conversion of your reactant, but that is a subject for our next class. What happens when you have reversible reactions? For time being, let us say that it does go up to 1. So, we are dealing with a irreversible reaction. Now, once again the conversion is tied down to species, unlike our extent of reaction which was tied down to the reaction. The moment we say that our conversion is related to species, the question arises, which species? Is it same for all species, or we define only for one particular species? Conversion is typically divided for only what we call stoichiometrically limiting species K. That is, it is defined for that species K which is stoichiometrically limiting. What do I mean by stoichiometrically limiting species? So, let us go back to our example of carbon monoxide plus hydrogen giving rise to methanol. So, in principle I can define conversion for both carbon monoxide and hydrogen in this example, but I am going to do it with basically one of the species which is limiting. Now, how do I decide that limiting species? The idea is very simple. Let us say that we started with 1 mole each of carbon monoxide and hydrogen. So, my Nj0 was 1 for both these species. Now, can I get, for example, for carbon monoxide Nj equal to 0? That means, can I have complete conversion of carbon monoxide? No, because if you look at the stoichiometric coefficients of carbon monoxide and hydrogen, to completely consume 1 mole of carbon monoxide, I need 2 moles of hydrogen, but I had only 1 mole. That means, in this example, my hydrogen is the limiting species, because my reaction will stop moment my hydrogen is exhausted from the system, and therefore, I refer to hydrogen as my species K, that is the limiting species. How do I find out which is limiting? So, how did we find that hydrogen is limiting? So, we look at the ratio of Nj0 and νj. So, for example, Nj0 by νj for carbon monoxide and negative of that would be 1, and for hydrogen it will be half. That is 1 mole we started with stoichiometric coefficient 2, and we look for minimum of these ratios 1, half. So, if there are more species, we will look at each of these ratios Nj0 by νj, and the minimum ratio, that is the ratio for the species for which this ratio, this quantity is minimum, is my limiting species. So, I have now a concept of limiting species, and this conversion is referred to in terms of that limiting species. So, for example, if this was the condition under which I am doing this reaction, 1 mole of carbon monoxide and 1 mole of hydrogen, my limiting species is hydrogen, and moment it gets 100% converted, the reaction will stop. There will not be complete conversion of carbon monoxide, because 0.5 moles of carbon monoxide will still be remaining, because 1 mole of hydrogen can only utilize 0.5 moles of carbon monoxide, and we will get only 0.5 moles of hydrogen. So, this is all about basic representation of a reaction and monitoring of its conversion. Now, how do we use this information? So, let us go back to our example of ethane or ethane cracking to ethylene, and let us say that we are doing this reaction in a tubular reactor. The real reactor does not look like this, but this is only schematic, good enough for our purpose. And let us say that there is certain flow in terms of moles, that the gas is entering in the reactor, and there is a certain flow, it is coming out of the reactor at the exit of the reactor. So, one of the first steps in design equations that we saw at the first beginning of this class that we have to do is actually relate these flow rates in terms of either extent of reaction or conversion of reaction and so on. And the way we do that is by setting up the stoichiometric table, and this is done in the following manner. It is a very systematic approach which is illustrated here. With the reaction, let us say involves 4 species. So, nu1 A1 plus nu2 A2 plus nu3 A3 plus nu4 A4 equal to 0 is my reaction. I have a table here. First column is the species, corresponding molar flow rate at the entry of the reactor, how much has changed in the reactor rather, and what is at the exit of the reactor. For sake of simplicity, I am going to assume that my species A1 is my limiting species, and I am going to define my conversion of this species in terms of the molar flow rates of this species A1, or in other words, I am going to define my conversion x as F10 minus F1 divided by F10. So, let us quickly go through this table. It is just nothing but bookkeeping of what is happening in the reaction. So, if I am looking at species A1, then I have F10 that is coming in. What has changed in the reactor is F10 times x, and what is coming out of the reactor F1 is F10 minus F10 into x. For all other species, Now, I can write the corresponding molar flow rate in terms of this key species and its conversion. So, let us say we are looking at any species J, AJ, for which entry flow rate is Fj0. The change now will be, recall that we have a stoichiometry to worry about. So, if F10x moles of A1 has changed, then nu j divided by nu 1 times this F10 into x is what species J has changed. So, the change in number of moles of jth species is nu j by nu 1 into F10x. It is true for all remaining species 2, 3, 4, and we have Fj as Fj0 minus nu j by nu 1 into F10 into x. For sake of argument, and because for ethylene example there was steam, and steam is like a inert. So, if I had inerts coming in at a rate F10 changed, F1 equal to F10, that is inerts do not change. So, number of moles of inerts coming in and going out are same, there is no change. Then we can sum up all these species and write what is the inlet flow rate, what is the outlet flow rate, and we write outlet flow rate in a compact form. Ft as total Ft is Ft0, that is what is coming in, plus this delta which is this minus nu summation nu j by nu 1 into F10 into x. So, this is my stoichiometric table. Where do I use this stoichiometric table? Remember, we are dealing with, if we are dealing with gaseous reactions, then there is a change in number of moles as the reaction proceeds. For example, in our ethane example, ethane to ethylene, starting with one reactant mole, we are getting 2 reactant moles of product. So, there is a change in number of moles. In fact, this summation nu j term will, this term over here summation nu j will reflect that what is the change in number of moles. So, if there is a change in number of moles, we have to now write for concentrations in terms of conversions for a reaction in which there is a change in number of moles. Of course, concentration has to be written in terms of conversion irrespective whether there is a change in number of moles, but some additional complexities arise if there is a change in number of moles. And let us say that we use equation of state PV equal to, in this particular case for a flow reactor, PV, V here denotes the volumetric flow rate, is Ft into RT if it is an ideal gas law, that is, this is at the exit, this is nothing but ideal gas law if this factor, compressibility factor Z is unity. But a general equation of state we can write PV equal to Z F RT at the exit of the reactor, at the entry of the reactor. So, subscript O denotes the entry. Notice now I can combine these two equations and that will result into volumetric flow rate V at the exit of the reactor is different from volumetric flow rate at the entry of the reactor because pressure, temperature and flow rates are changing along the length of the reactor. So, what we are essentially saying is, suppose this is my entry point and I have reaction and exit point. Between entry point and exit point, my pressure may be changing. Why? Because there could be pressure drop along the length of the reactor. My temperature may be changing because there is associated heat factors, or by molar flow rate may be changing. Why? Because there is a change in number of moles, and as a result of all these factors, my flow rate of entry could be different than flow rate of exit, and I need to relate these quantities. So, this is the first step in that direction. Now, pressure and temperature, to write to know how pressure is changing along the length of the reactor, what do you need? You need momentum balance. We will come to that little later on. For knowing how temperature is changing along the reactor, we need energy balance. What we have currently is only information about how flow rate is changing, molar flow rate is changing between the entry and exit, and this is from that stoichiometric table earlier. So, we have inlet molar flow rate and exit molar flow rate Ft and Ft0 related to each other through this set of equation. Ft by Ft0 in its final form we will get 1 plus epsilon x. So, this epsilon actually is nothing but this factor delta which we talked about earlier, and this y1 0. So, if we put these two information together, we now get, that is, substitute for Ft by Ft0 in this particular equation, we get volumetric flow rate changes along the length of the reactor in this particular manner. I will quickly wrap up our today's lecture by saying that this information in turn is related to the concentration changes. So, let us define the concentration at the inlet as molar flow rate divided by volumetric flow rate. So, moles per liter, moles per minute divided by liters per minute, giving rise to moles per liter. Same thing at the exit, F1 by V, where we know this F1 is related in terms of conversion and volumetric flow rate V. Now, for V we use the previous equation where we had this variation along the length of the reactor. If you put all these together, for my key species, concentration C1 changes from its inlet concentration, which is dependent on the conversion, which is dependent on how pressure changes in the reactor, how temperature changes in the reactor. And similarly, we can write a similar equation for all remaining species 1, 2, 3, 4, 5 up to n, whatever species that are there, and express concentration in terms of conversion. So, now let us summarize today's class. What we saw today was basically how to represent a reaction. We are just getting into our reaction engineering. So, the starting point naturally is how to express our reactions. Some of the keywords that you heard in today's class are stoichiometric coefficient, those numbers which tell you how many moles of carbon monoxide reacts with how many moles of hydrogen to give how many moles of methanol. We also talked about more than one reaction possible, so multiple reactions. But when you have set of multiple reactions, we need not all reactions, but only independent reactions. So, we have rank of the stoichiometric matrix telling us what is the number of independent reactions, and then we defined two ways in which we can monitor the progress of the reaction, namely extent of reaction and the conversion, and finally how we put all these information together to develop stoichiometric tables, so that we can eventually use them in our design equations. So, this is as far as the stoichiometry is concerned. In the next class, we are now going to get into thermodynamics, because if you recall, I said conversion may not go to 100% for certain reactions, certain reversible reactions. So, our next lecture will be focused on looking at reversible reactions and what information we get out of thermodynamic properties of our reacting system. Thank you.